All right, so in this presentation for my honors option project, I'm just going to cover some of the basics of encryption and an example algorithm used. So during one of the first lectures for this class, I remember briefly discussing how the internet was built on trust. As the internet grew and gained more users, it became clear that trusting that everyone has some degree of altruism would not be sufficient. Though the internet is still held together by trust to a certain degree, people no longer assume that the peers in the network have their best interests in mind. So this raises the question, how do we, the users of the internet, protect our personal information that we move around on the network? Well, one answer to this is encryption. At its core, encryption is simply scrambling data so only specific users and groups have access to it. Technically, encryption takes plain text data and converts it into what's called ciphertext, which is essentially a string of characters that is meaningless to humans. This name comes from the practice of ciphering, where parties communicating would switch letters around based on a pattern that only they knew to make messages unreadable to anyone that did not also know the pattern. For example, if I were to set up a simple cipher, I could map A to C, B to D, C to E, and so on. Or I could set up a cipher like the one in this presentation where B maps to E, C to F. There are a lot of ways to set this up. But even with a pattern like this, it's rather trivial. It would take a matter of minutes to write a program that could iterate through a sentence and check for every variation of this shifting. Also, computers do not store data in the form of plain text, or at least they don't store it in the form of like strings of characters. They store it in the form of strings and ones and zeros. So with this, modern day researchers have created incredibly sophisticated encryption algorithms. These algorithms are so sophisticated, in fact, that it's usually impossible to solve them with brute force. Using a brute force method, one would design an algorithm to iterate through a massive number of guesses until one of them resulted in a readable message. So algorithms now are so complex that you just can't do this. Um, so this may work for cipher mappings in the past, but this does not work for modern day encryption algorithms that are used today. So before we take a look at encryption, it'd be helpful to understand just why it's so important. First off, encryption is a solution to a variety of privacy concerns. By using encryption, people can rest assured that only people that can access their data are the ones that have explicit permission to do so. For example, if you're communicating with your doctor about a private medical issue, would you really want pharmaceutical companies to be able to push advertisements to you based on these communications? If you're unhappy at your current job and were exploring new opportunities, would you want your employer to be able to intercept your private messages and discover this? Of course not, which is why encryption is so important for communication services like email, for example. Another reason to incorporate encryption into any application or system that contains sensitive data is security. If a data breach occurs, one can rest assured that their encrypted data is still safe. For example, if an employee leaves his or her phone on the subway, the company can rest assured their data is safe if they have chosen to encrypt it, even if his phone is stolen, goes missing. Encryption can also make man-in-the-middle attacks, which we studied earlier in this semester, which an attacker tries to alter the information sent between two parties, nearly impossible. Another benefit of encryption is authentication. With this, we can make sure that the people we are dealing with are actually who they say they are or claim to be. This is done with something called an SSL certificate, which we will get to shortly. In addition to all of this, regulations in certain fields simply require that users' data is kept secure. An example of this is HIPAA, which is followed in the medical field. Considering all of this, it should be clear that encryption is necessary in almost every application and service that we use today. Now that we understand the value proposition for encryption, we should be sufficiently motivated to at least gain a basic understanding of how it works. An important concept in encryption is that of keys. A key is simply used to lock, or encrypt, or unlock, which is decrypt, data. Some types of encryption use the same key to both lock and unlock data. This type of encryption is called symmetric encryption. Though it is usually more efficient, it is generally less secure. Other types of encryption use two keys, a public key for encryption and a private one for decryption. This is called asymmetric or public key encryption. Usually, either of the two keys can be used for either function, but once one key is used, the other is bound to the next function. For example, let's say I have two keys, A and B. If I want to send a message to my friend David, I can encrypt the data with key A. If I do this, then my friend David must use key B to decrypt the data. This technology lies at the foundation of SSL, a massively important protocol. Encryption is done with an encryption algorithm, which, like any algorithm, is just a series of instructions that tells a computer how to convert plain text into ciphertext. Some common encryption algorithms include the Data Encryption Standard, DES, Triple DES, which is the newer version of DES, and RSA, the last of which we will cover in detail at the end of this paper. So one protocol that uses encryption is HTTPS, which is simply the HTTP protocol with SSL, secure sockets layer, built on top. Actually, they may refer to this additional layer as SSL. It's really something called TLS, or Transport Layer Security, which is just a newer version of the now deprecated SSL. TLS has three basic components: encryption, which we've covered, authentication, which we've covered, and integrity, which deals with making sure that data remains unchanged in transit. Any communication with this protocol starts with a TLS handshake that establishes a cipher suite, which is a set of algorithms that specifies detail about the session's keys. This handshake handles authentication via public key encryption. After this, the client and server transfer keys. The client also uses a public key to generate a pre-master key, then sends it to the server. The server decrypts this with a private key, and the new key computed by both the client and the server functions as the master key, which is used to decrypt the data. If this seems too complex, just know that asymmetric encryption, or public key encryption, is used at first, and then symmetric encryption is used for the rest of the communications. Then, the data that is being sent is encrypted with a number of algorithms signed with a message authentication code, or MAC, not to be confused with a MAC address, and sent. Then, the client can use their copy of the master key to decrypt the data and check the MAC code to make sure the data has not been altered, verifying its integrity. So now that we kind of understand how TLS works, we can begin to understand HTTPS. The value proposition for HTTPS is such: it is more trustworthy for users, it is more secure, and it helps authenticate websites. Traditionally, the HTTP protocol is used when one wants to access a web page. If a server wants to implement HTTPS, they simply need to implement TLS on top of their existing HTTP protocol. If they do this, they can obtain an SSL certificate from a third party called a certificate authority. This certificate is hosted on a website's origin server. It contains info such as the domain name, the length of the certificate is valid for, the public key algorithm, version of TLS being used, and something called a thumbprint, or a fingerprint in this visual, which is kind of a hash of all the data in the certificate, like a unique signature. If a client makes a request to a site using HTTPS, the browser will search for the certificate on the site's origin server. This security protocol allows users to know that their data is being sent to and from their data that is being sent to and from a website is secure. At this point, HTTPS is widely used, and some browsers even refuse to load pages that do not use this protocol. So now that we understand encryption and one of its applications, let's look at a specific encryption algorithm called RSA. This algorithm deals specifically with the problem of sending encrypted messages to a party of which you've had no previous communication with, which is one problem with public key or asymmetric encryption setup. This algorithm is widely used, especially in tandem with other symmetric encryption algorithms. This is because the public key setup is quite resource heavy. Now let's jump into exactly how RSA works. This algorithm uses something called trapdoor functions, which are easy to compute in one direction, but seemingly impossible to compute in the other. For example, if I told you that 23,213 was the product of two prime numbers, you would have a very hard time figuring out which two numbers these are. But if I asked you to calculate 139 times 167, or told you that 136 times some other number resulted in 23,213, you would have no problem. These functions are how algorithms like RSA share public keys. The first step of RSA is generating the keys. To do this, we need two prime numbers, P and Q. These are selected with any number of sophisticated algorithms which are outside the scope of this paper, so just know that they need to be both large and far apart. In this example, we'll use smaller numbers for the sake of simplicity. So, let P equal 139 and Q equal 167. Now we need to find the modulus, n, which can be represented with n equals P times Q. So n equals 23,213. Now we can generate our public key. An important thing to note is in this I'm representing Carmichael's totient function with C of n. It's usually lambda n. I just chose to use C of n for this presentation and paper. So now with this, once we find this function, we can generate our public key. which is made of a prime number, e, and n, which we already have. E can be anything between 1 and c of n, but generally e is set to 65,537 to keep things efficient because a public key is shared openly anyway, so it doesn't really need to be chosen randomly. Now for our case, just to make things simpler, let's use a much smaller number. So let e equal 7. We can derive the ciphertext c from our plain text m with the formula c equals m to the e mod n. And for our message, let's choose something simple. So let m equal 17. Now we have c equals 17 raised to the 7 mod 23,213. We can calculate this out, and we see c is 2,472. So now what we have is our ciphertext C. This is the encrypted message, so we could send this to any receiver and rest assured that the data is being kept private or encrypted. So for the private key step, private keys are made of D and N, and we have N, and the formula for D is such: D equals 1 over E mod C to the N. Now it's important to note that this is not the regular modular function, but it's something called the modular inverse, which is pretty outside the scope of this paper, but luckily there are online calculators for this, so we can just plug the numbers in. And we have D is 1 over 7 mod 11,454. And then solve that. D comes to 4,909, which function is our private key. So now we can use this private key to decrypt the ciphertext. So we can do this with the formula: M, or the message, is equal to C, or the ciphertext, raised to D, private key, mod N, which is our modulus. So plug these numbers in. Now, of course, there aren't really any calculators online or normal calculators that could take a number out to the 4,909th power, but luckily there are online calculators for this algorithm specifically, which I'll link to in my paper. So we plug these numbers in, and we see m is equal to 17. So it works. That's kind of the basic way you would encrypt a message with a public key and decrypt it with a private key. And of course, even more complex strings of characters, like full sentences, work the same way, because under the hood, it's all stored as ones and zeros anyway. So you're just dealing with numbers. So, by no means exhaustive, I hope this paper serves as a primer for the field of encryption by explaining its value propositions, a few of its applications, and an example of an algorithm for encrypting messages. Thank you.